Welcome everybody to the third lecture in transmission lines. In this lecture, we'll be talking about more realistic transmission line circuits. So far, what we studied was almost like this side of the transmission line. We concerned ourselves in the beginning with lossless transmission line and with the load side of the transmission line only. Like in this lecture, we'll be concerned with the losses in transmission line as well as the generator side of the transmission line as well. So what we studied so far was about the reflection coefficient here, or the boundary condition at the load. The boundary condition is at the load is V at the load divided by the current at the load must equal ZL. From this boundary condition, we got the expression for the reflection coefficient at the load. When we consider the generator side, we'll have another boundary condition. The boundary condition at the generator side is related to the input impedance, as we're going to see shortly. So in order to study a complete sort of transmission line circuit, let us analyze this circuit that we have right now. So as I said in previous lectures, we have the general expressions, and to come up with a real solution for this circuit or any other circuit, we use the boundary condition to find the solution. The boundary condition at the load is V load divided by I load equals ZL. From this boundary condition, we got the reflection coefficient, which has a definition of reflected wave divided by incident wave. The amplitude of reflected voltage wave divided by the amplitude of the forward magnitude of the forward voltage wave. So as we used in previous lecture, we will put the zero here. This is the positive Z, so the wave propagating in this direction is positive. This is the negative Z, the wave propagating in this direction is negative. When the wave reach the load, part of it will be reflected, and this is gamma L, gamma at the load, and gamma at the load is related to gamma at the input. So gamma at the input is gamma minus L. Sometimes we write it L for just for short writing, but we know this is the negative Z direction and this is the positive Z direction. Gamma N equal gamma 0 or gamma load multiplied by e to the minus j beta L, or gamma L e to the minus g beta L. At the input impedance equal V of L divided by, here we didn't use minus L for short writing, V divided by I equals Z input. And we previously, in previous lecture, we came up with this expression, which also can, after substituting this N, we can write it in this format as well. So those two formats are equivalent to one another, and this is the input impedance at the input of the transmission line based on its length. At any point on the transmission line, we are considering two components of wave, a component propagating in the positive or forward direction and a component propagating in the negative direction. They are related at the zero, because this is zero. They are related with this expression. So at any point on the line, we can express the total voltage as V node plus e to the minus j beta Z, a component propagating in the positive Z direction, plus gamma L, the reflection coefficient at the load, multiplied by e to the j beta L, So there is one Z missing here. Let me put it. So this is a component of the wave propagating in the backward direction. Also here we would like to notice that we start to write gamma L, because there is other gamma, for example, like there is gamma G that we're going to introduce shortly, so that we start to put subscript for the reflection coefficient. And that is why is this? It's just because we are now analyzing the full circuit. In previous lecture we're just having one reflection at the load, and we assumed in previous lecture that the generator is matched. And one thing also to notice here is that this part here is sort of like a lumped circuit. It's a regular circuit. So in the book, like they draw like the gamma G to be similar to this, which is wrong. So the notation, or just the shape of the definition of gamma G in the book, is wrong. The wave is incident on the generator, and part of it, gamma G, is reflected. So it should be like this one. It should be expressed like this one, not the other way, like not the way in the book. Just like the sign or like the symbol here is correct, the symbol in the book is not correct. Okay, so at the generator side, so here at the input, we have V minus L does have this expression, V minus L. So this is Z input here. So the equivalent circuit for this would be VG, like powering ZG in series with Zn. So the current going out of the generator is VG divided by Zn plus Zg, and the potential here at this point equals Zn. So it's just like a potential divider between Zg and Z input. So the boundary condition at the load is here. V at the load equal Vg multiplied by Zn divided by Zn plus Zg. So we can rewrite from this equation here, we can rewrite the expression as such. So we're just writing V positive as a function of V minus L, and we are just like going here. So we have, like, if we write V plus equal V minus L divided by this expression, but V minus L does have this expression, so V plus equal VL, this part, divided by this expression, but we took e to the minus j beta L out and put it here. So we have this expression. This expression can be rewritten in this format by the substitution of expression of Zn. So we substitute Zn in both like places here. We can rearrange this expression to express V plus V naught plus the incident on the load, and related to the generator, the Zg, the length, the reflection coefficient at the load, and the expression for Zg at the generator. So at the generator, what we see from here, we see a load of Zg, and our characteristic impedance is Z naught. So the reflection coefficient here is gamma G, which is the reflection of like the voltage incident. Here is a negative voltage, and the reflection would be the positive voltage. So it's V0 plus divided by, V minus L plus divided by V minus L negative. So some wave is incident in this direction, part of it will be reflected, which is gamma G. So this is the expression for like the whole circuit analysis, and this part here is just like a lumped element. There is no wave propagating or anything. It's just like lumped element. Actually, it is not two elements, just one element, and any source, any generator does have its internal impedance, which is represented here by ZG. So one very important thing when we do like a full analysis for a circuit is the power flow. So the standing wave ratio equal Vmax divided by Vmin. It does have the same expression as before. So when we considered the generator, nothing had changed, and I'm asking you why it didn't change. Just think about it, and we can like remind me to discuss it in the discussion session. So regarding the power flow, we need to discuss the power delivered to the load. So the power delivered to the load is, because it's an AC power, we are talking about the power equal the real part of V at the input multiplied by the conjugate of the current at the input. So just taking Z input into consideration, so it's a half V input square, the real part of 1 over Zn, because In is V conjugate divided by Z, and the real part of 1 over Z or 1 over Z conjugate is the same. So this is the expression for the power delivered to the load. So we can like write it in terms of Vn, or we can write it in terms of generator voltage. To do like further analysis, let us write Zn as a real part plus J imaginary part. Same thing for the generator internal impedance. So the power delivered to the load in this case would have this expression. I suggest to you that you prove this yourself. So like how this expression came in. What we are behind is the real part of 1 over Zn. So if we write it, so it's from here, and we need to like come up from this expression. How can we reach this expression? I suggest that you like do this derivation yourself, just to practice more about complex number manipulation. So in case of like matched load means ZL equals Z naught. So there is no reflection coefficient. Standing wave ratio will equal 1. Z input equal Z naught, because it's matched at any point irrespective of the length. We will have input impedance equal characteristic impedance. So the power delivered to the load in this case of matched load does have this expression here. We just bought ZL equal Z naught. So if we have like a case of generator matched to the transmission line, which means Zn equals Zg. So here this is an important thing. Matched to, like when the generator is matched to the circuit, it means Zn equals Zg. It doesn't mean that Zg equals Z naught. So this is important here. The input impedance, when we say like matched to the generator, it means that Z input equals Zg. So we can write the expression for Zn. It has a real component and imaginary component. And if we write down the expression, we'll find it this way, because Z input equals ZG. ZG does have a real component and imaginary component, like this expression. If Zn equals Zg, so this will be 2Rg, and this will be 2Xg, which is the case here, and we have the expression. So now we studied two cases: a case of matched load to the transmission line, ZL equals Z naught, and a generator matched to the transmission line, Zg equals Zn. In both cases, we are seeing different value for the power delivered to the load. This is just like taking us to the question, what is the optimum load impedance? Or what is the impedance of the load that would achieve maximum power transfer from generator to the load? So we need to maximize this expression here, the general expression here. We want to maximize this expression. So we have two parameters, Rn and Xn. In order to optimize the expression, we'll like make a partial derivative with respect to Rn and partial derivative with respect to Xn, and equate the derivative, the partial derivative, to 0. So the partial derivative with respect to Rn will give us this expression. In order for this to equal 0, we'll have equation 1. Partial derivative with respect to Xn, for this to be maximum, for the power to be maximum, we need this to equal 0. So we have the second equation here. Solving those two equations together, we will get like the conditions for maximum power flow, maximum power delivered from the generator. Maximum power delivered from the generator to the circuit is happening for the case when Xn equal minus Xg, Rn equal Rg, which means that Zn is the conjugate of Zg. Under this condition, there is a maximum power transfer to the load, or maximum power transfer like going out of the generator. And the maximum power, when the maximum power is achieved, the power delivered to the circuit, or the power taken out of the generator, does have this expression. So this value is the maximum power available by the generator under the conjugate matching condition. Gamma L and gamma G are not necessarily 0. So the maximum power out of the generator doesn't mandate, doesn't require matched load, doesn't require matched generator or anything. So it's just like a unique sort of condition for maximum power flow. Now we're gonna move to like another topic about real transmission line circuit, which is lossy transmission line. So in reality, all transmission line does have losses. The source of losses are two. Losses from the conductor, because there is no perfect conductor. Any conductor would have some ohmic losses, which we sort of like represented in the RLCG lumped element model by the resistance. Also, the other part is the dielectric material. Any transmission line must have a dielectric material between the two conductors, and this dielectric material is not perfect insulator. It does have also like some losses, and we like represented these losses with the G in the like the lumped element model. Even though we know that the losses in the transmission line is small, but in many situations the losses of the transmission line is important and shouldn't be neglected. That's why we are studying the effect of the losses, or how to model or express the losses of the transmission line, even though we know ahead it is very small. So in the case of small losses, there is some very common approximations that we do to simplify the expressions, that we're gonna do this right now. So the general expression for the propagation constant gamma is that it's composed of two parts, attenuation constant and phase constant, and it is related to this expression here. We are using the lumped element model that we discussed in the first lecture about transmission line. So this can be like rewritten or rearranged as such. So this one here is the one that we like use frequently, or like use when the case of neglecting losses. For neglecting losses, we said that we can assume R is negligible, so we can put it 0, G is negligible, and we have just this expression for lossless transmission line. When there is a losses for the transmission line, so we have this part here which can rearrange this one and write it this way. We know that the approximation is coming now. We know that R is small compared to L, G is small compared to C. So RG is very small, sorry, R is small compared to omega L, G is small compared to omega C. So RG is very small compared to omega square LC. So we can neglect this part, and for the other part we can use Taylor series expansion to approximate this. So the first order approximation for this like propagation constant is using like this Taylor series expansion. We neglect higher order terms, so the expressions that we have does have this format for the propagation constant gamma. The first part here is the phase constant. The second part here will be the attenuation constant, which does have this expression, and we are approximately saying that Z0 equal L over C. So for first order approximation, we take the losses into consideration for the propagation constant, but we didn't take R and G into consideration for Z0. If we take it for Z0, Z0 will not be real, it will be a complex value, and the analysis would be more complicated. So like the zero order approximation, assuming ideal transmission line, first order approximation, we assume real characteristic impedance with complex propagation constant. And if we are to analyze like the circuit even like more accurately, we can take Z as a complex quantity and like solve the problem. Of course, there is simulation tools that take all of this into consideration, but for like hands calculation or for intuitive understanding of the circuit, this level of approximation is enough. So we're just saying here that Z0 and beta for low loss transmission line are the same as the case of lossless transmission line, and this will simplify a lot of the analysis and make the stuff that we learned so far applicable for a wide range of problems or applications. So this method of approximation that we're using is called like perturbation method, and we're gonna see how it is used in the next slides. So in this perturbation method, as I just said, we'll assume that the Z0 is real, and we solve the problem the same way that we solve it for lossless transmission line. The only difference is instead of using J beta, we'll use alpha plus J beta. So VZ, the voltage at any position along the Z axis, equal V naught plus e to the minus J beta Z, the forward e to the minus gamma Z. This is the forward propagated wave, and plus gamma e to the gamma Z, which is the backward propagating wave. For the current, it has a forward propagating plus a negative propagating, but the relationship between V plus and Z naught, V plus and I plus is 1 over Z naught. For V plus and for V minus and I minus, it is minus 1 over Z naught. We did this explanation in the first lecture on transmission line, so that's why we have a negative sign here for the current. So we know that gamma equal alpha plus J beta, so the gamma at the input equal gamma at the load multiplied by e to the minus gamma to gamma L. So now we can separate this one. So this is an attenuation, so gamma will not be like a constant across the line. It is changing across the line in magnitude as well as in phase. So if you see like any analysis like this on the Smith chart, you will find that it's like a helix. The further you rotate or the further you move on the transmission line away from the load, the reflection coefficient will keep shrinking and moving in a spiral rather than moving on a circle. But we are not using the Smith chart in our course to solve lossy transmission line problem. So from the expression of gamma at the input, we can come up with the expression for the Z input, or we can just like repeat the expression or reuse the expressions that we had before, just replacing J beta with alpha plus J beta. So we'll have this expression or that expression. Notice that here it is tan H, which is a hyperbolic tangent expression for gamma L. Before that we were having J tan beta L, but now this is the expression for lossy transmission line. The power input, the power delivered from the generator to, or like the power at the input, equal half real part of V input multiplied by the conjugate of the current, which can, like when we substitute this quantity here, it will have this expression. So from Vn and In, we can have this expression here, and we can also like rewrite it this way. If we take this outside, and this is gamma L, so gamma L does have this component here. So if you take this expression out, this will be e to the minus 4 alpha L. 4 alpha L, so here this is the magnitude of gamma at L, gamma at the input. So the square of it will be e to the minus 4 gamma L. So this is the expression for the power input. Shortly we'll know why I had put this into this format. So the power delivered to the load, we're taking this expression here, the power delivered to the load, it can be expressed like this. From V plus, this is the power delivered to the load. So now if we want to calculate the power lost on the transmission line, it's the difference between power at the input, it will be like certain amount, some losses will happen, then the remaining will be delivered to the load. The difference between power in and power delivered to the load is the losses. If we just do the math, we'll find that B losses does have this expression. So the first term accounts for the power loss of the incident wave. The second term accounts for the power loss of the reflected wave. So if you look here, this component, this is the power loss for reflected wave, this is the power loss for the incident wave. Of course, here you can just like review the math about these two values, and both terms will increase as as alpha increase. So the more losses, the higher the loss constant, the attenuation constant, the higher the losses will be. Some other topic of interest is sort of like the distortion on transmission line. So in general, let me just do this, okay. So in general, the propagation constant of a lossy transmission line is complicated function, as we can see. So it has this expression. So if the transmission line is lossy, beta will not be a linear function of frequency, which means that for different frequency we have different propagation constant. This kind of behavior causes a distortion to the signal, and this distortion is very important. It's called the dispersion of the transmission line. So dispersion is a phenomena that is happening on transmission line, on fiber optics, and it is caused by the fact that different frequency, the signal of different frequency does have different phase velocity. So what happens when we have a dispersion? It's like, okay, let us assume that we are sending this signal. This is the shape of the signal in frequency. So we divide them into like those 7 different bins of frequency. If each bin does have a different speed over time, so if this is the fastest speed and this is the slowest speed, so the further it travels, this one will travel faster than this one, and we have this spread of the signal or dispersion of the signal. The signal can start sharp like this at the receiver. After a time it will spread. When it spread, it causes like intersymbol interference, and so now the signal or this pulse is supposed to occupy certain period of time. Now it's occupying more, which means it will interfere with the symbol after and the symbol before, causing intersymbol interference. And this phenomena here is called dispersion. So the signal can start like this and it gets spreaded. So this here, look to the difference. So over time we need to have like transceivers, something that receives the signal, correct it, and resend it again. This is very famous problem on high-speed digital design. This is an important problem in fiber optics. So on different kind of transmission line, the dispersion is an issue that need to be considered, and the source of this is the phase velocity variation with respect with frequency. So some transmission lines doesn't have this problem, and it's called like a distortionless transmission line, and this happens if the ratio between R and L equals the ratio between G and C. In this case, the phase velocity will be linear, does have a linear dependence on frequency, and alpha will be independent of frequency, and this transmission line is called distortionless transmission line. So for distortionless transmission line, beta depends on frequency in a linear way, so the phase velocity is constant, and alpha, which is this value here, is independent of frequency. So like it's important to know about the dispersion, the cause of the dispersion, and the special case of distortionless transmission line. We talked briefly before about the transient on transmission line. So on transmission line, all like what we had studied so far is sort of like the steady state. But in some cases, especially in digital communication, the transient, or like for digital circuit in general, the transient of the transmission line is an important topic, and it's important to understand and be able to analyze the transient on a transmission. So in some situations, like when we have like short pulse, very short pulse in time, short in time, is translated into a very wide band in frequency signal, and the transient in this case is sometimes important and needed, and this is what we're gonna study now. Okay, like to study the transmission line transient, like a circuit here, the circuit shown in figure like is connected to a DC source. The source is switched at time equals 0. So we have a DC source. When you connect, so the idea is to just like have a pulse. We need to like first consider like some information about like the behavior of the signal on transmission line. We shared this before with you, but let me say it again. So the most important thing here is what we shared before. The wave propagating on transmission line doesn't see the future. It just sees the situation at its position and behave accordingly. So when we switch this on, the signal behaves the same irrespective of the load impedance, irrespective of the length of the transmission line. Why? Because when we switch this on, the signal is here, the signal sees nothing but here. So when we talk about transient analysis, what we see is not Z input. What we see is Z naught. This is the transient analysis. If we are like doing the steady state analysis, the signal, similar to what we did so far in the course, the signal will see Z input. But for transient analysis, the signal doesn't see the future. Where is this Z input came from? Z input came from ZL and the length of the transmission line. So as we like did the analysis before, when we talk about the reflection coefficient, we can calculate the reflection coefficient from transient analysis. So here we are doing this again. So at time equals 0, we switched this on. So remember, this part is a lumped element part, so it doesn't have like a physical dimension or length or anything, but we're just drawing like this to show that we have a source, and this source does have an internal impedance. So when we switch on, the load seen by the source is just Z naught. So we'll start by a very simple case of a matched transmission line, and we assume that at the beginning, at time equals 0, the potential on the line equals 0, and we switch it on like this switch at time equals 0, and we want to analyze like this problem. We need to see how the voltage change with time over any point on the transmission line. So at time equals 0, what do we see? Okay, when we switch on this switch here at time equals 0, V naught will see two impedances, Z naught, which is its internal impedance, and the characteristic impedance of the transmission line. It is not the input impedance. We see the characteristic impedance of the transmission line. So the potential seen at time equals 0 here start before 0. It was before time equals 0, the potential was 0. At time equals 0, when we switch it on, we start to see the potential here. The potential we're going to see is a potential difference value, which is V naught divided by 2. This potential will propagate with the phase velocity till it reach the load. So at time equals 0, we have the potential here equal V naught over 2, and it's 0 everywhere else. So everywhere else is 0 except at this point. After some time, the signal is propagating. So like V naught over 2 is reaching here, reaching here, reaching here, reaching here. At the time of L over VB will reach the load. So at this time it will reach the load. The load is matched, so there is no reflection. So the signal will start at 0 with the value V naught over 2. Over time, this voltage will propagate till it reach the load, and there is no reflection, so we reach the steady state. The steady state is that the potential everywhere, the voltage everywhere on the line is V naught over 2, and this steady state had been reached at time equal L, the length of the transmission line, divided by VB. So from next examples, we'll learn and understand more. So let us go on. So now let us study this case, which is a transmission line terminated with a short circuit. So at time equals 0, as I said, we'll have the same behavior because all what the source see at this point is the characteristic impedance. So before time equals 0, everything on the transmission line equal 0, no potential on the transmission line. At time equals 0, we switch it on the switch, so the potential at this point will equal V naught over 2. Where is this V naught over 2 came from? It came from Z naught in series with the characteristic impedance, not the input impedance, the characteristic impedance of Z naught. And this potential starts to propagate. So the potential V naught over 2 is propagating with the speed of VB, phase velocity, till it reach at the short circuit, at the load. At the load, there is a mismatch, so there will be reflected wave. The short circuit is 0, so the reflection coefficient is -1. So there is a forward propagating signal of V naught over 2. It's propagating from time equals 0 till the time of L over VB. It reached here. At this point, we are generating a backward propagating signal with the amplitude of minus V naught over 2, because the reflection coefficient is -1, and this signal starts to propagate. So at this time, the potential here, a little bit before reaching the load, it was V naught over 2. After reaching the load, there is a reflection of minus V naught over 2. So at this moment, the potential here starts to be 0. And with the propagation of the reflected wave, it is getting 0, 0, 0, 0, till we reach this point, which takes us 2L over VB. When we reach it here, like all the line will return back to 0. So at time equals 0, the potential start to propagate, V naught over 2 start to propagate. After reflection, this V naught over 2 start to become 0 as the reflected wave is coming till the reflected wave is reaching here. Then we reach the steady state of all the line filled with 0 potential, and this steady state is reached at 2L over VB. Let us consider the other case of open circuit terminated transmission line. At the beginning, at time equals 0, it is the same. No difference. The source sees internal impedance in series with characteristic impedance Z0. So we have V naught over 2 that is propagating over the transmission line. At the time of L over VB, the signal reached here. It meets an open circuit. For the open circuit, the reflection coefficient is +1. So another wave, backward wave, started at the time of L over VB, and it is propagating backward. So at any point, the total voltage on the line equals the forward wave plus the backward wave. The forward wave is V naught over 2. The backward wave is V naught over 2. So at this point, we start to see V naught, and this V naught is propagating till we reach the source again at the time of 2L over VB. And at this time, we reach the steady state. The steady state is the whole line is filled with potential equal V naught. A good way to analyze this problem is called the bounce diagram. So the bounce diagram is a standard method to solve for like the transient of a transmission line on paper, of course. It is not the one used in simulation package. So here the idea is we are propagating. So this is the time, and this is the length of the transmission line. So at time equals 0, we start by 0. So here this is which case? So this is the case of the open circuit transmission line. At time equals 0, a forward signal is generated, and the forward signal does have the value of V naught over 2. It will reach the load at what time? At L over VB. So this signal at 0, before time equals 0, the potential everywhere equals 0. So this is Z equals 0, this is Z equals Z, this is Z equal L. At time equals 0, we switch it on, the switch. So a forward propagating wave is traveling. It will reach L at this time. So any point on the transmission line is represented here. So from time equal 0, this is time. From time equal 0, let me have a pen. Okay, from time equal 0 till this time, which is Z divided by VB. The point Z does have 0 potential. At this moment, it starts to have V naught over 2 potential. Then the wave propagate till it reach the load. At the load, it found an open circuit, so the reflected wave is the same magnitude as the incident wave. So another wave is propagating backward at any time from this time till this time. Okay, so from this point, the potential at point Z equal V naught over 2. The time from this point in time, the signal will go and come back. So at this point in time, we start to see a potential at point Z equal V naught. Why? Forward wave equal V naught over 2, backward wave equal V naught over 2. At any point of time, we are like summing up all the waves that reach this point. So this is the idea of the bounce diagram. So the bounce diagram, at this point, we start to see potential V naught over 2 at point Z, and at this point in time, we start to see a change in the potential from V naught over 2 to V naught, and after that we have the steady state. So this bounce diagram is used frequently to solve or just to visualize the timing or the transient on the transmission line. So let us see this example here. It will also explain the situation better. So we are requested to draw the bounce diagram for the transient circuit shown in figure, including the first 3 reflections. Okay. So here, notice that like the gamma G is drawn correctly in the book at this point. Okay, so at time equals 0, before time equals 0, the potential everywhere on the line equals 0. At time equals 0, we switch on the line. What does the line see at this point? 12 volt, the internal impedance is 50 ohm. It does see 100 ohm load, so the potential will be 100 over 150, which is 8 divided by 12, 100 divided by 150. So this is the load at this point is Z naught, the characteristic impedance, ZG, the source impedance, the potential is 12. So we have, at this point, we are launching a forward wave of 8 volt. It will reach the load at certain point in time equal L over VB. At L over VB, a backward wave will be generated. The value of this wave equal 8 multiplied by gamma L. Gamma L equal 1 over 3. So we'll have a backward wave of 8 over 3 traveling. It will reach the load, sorry, the generator. At the generator, we will see another reflection coefficient, which equal 50 minus 100 divided by 150, so it's minus 1/3. So another forward propagating wave equal minus 8 over 3, which is the reflection coefficient at generator minus 1 over 3 multiply the wave incident on the generator. This wave will propagate till it reach the generator, sorry, the load at this time, 3L over VB. It will reflect again with another 1/3 reflection coefficient. So we have reflection at the load, reflection at the generator, reflection at the load again, and we reach at this point. This is the bounce diagram. So if we want to draw the transient of the potential at this point here, it will look like this. Okay, let me Okay, I see it now. So over time we'll start by 0 for some time, then we'll have 8 volt. So this is the volt V, and this is time. So here we'll have 8, then it will remain 8 for a while from this point to that point. It will be 8, then it will be at this point here. So this is point 1, this is point 2, at this point it will start to be 8 plus 8 over 3 till it reach here. Then after a while it will go a little bit down, then we'll go again a little bit down, so on and so forth. So at the beginning it starts at 8 plus 8 over 3 minus 8 over 9 minus 8 over 72. So this is the transient of any selected point. So you can select this point, that point, and draw the transient of the signal on this transmission line. Homework 2 is due in a week, and the learning objectives of this lecture, and meet you in the discussion session shortly.